Hi guys, sorry I couldn't be here today. My wife had to have an operation first thing in the morning, so I can't be here. Otherwise, I would be here to help you with this. Today's topic is one I love teaching. It's called orbit. We all know that things orbit the Earth, and today we're going to try to learn why. And I'm not very good at doing these kind of screencasts, so forgive me if I say a lot and screw up. But I'm just not even going to stop. I'm not going to edit this, so it's going to be kind of rough. Uh, but let's just get going here. So the first thing to keep in mind is that. Uh, Objects, if they don't have any initial velocity perpendicular to the gravitational force vector, uh, here's what's going to happen. They're just going to fall straight down. So if I have an object that has zero velocity and I let it go, it's just going to fall straight towards the Earth's center. Because remember, gravitation is a force that attracts the center of one object to the center of another object. And it doesn't matter how much mass or how far apart they are, that force is going to exist. So if I just take the object and let go, boom, straight towards the Earth's center until it contacts the Earth's surface. But now if I give it some velocity horizontally, what happens is instead of falling straight towards the center of the Earth, it drifts sideways as it falls down. And so it's still trying to follow the center, but it's drifting sideways and it ends up impacting the ground over here instead of directly under where it was initially released. Now, if you think about this, if I just give it a little bit more horizontal velocity, what happens is quite interesting. If you give it sufficient perpendicular velocity, velocity perpendicular to the gravitational force vector, in the amount of time it takes to fall from its initial position to the center of the Earth, it's going to drift so far sideways that as it falls this way, it drifts this way, so it ends up taking this path here. And now look, when it got to here, it has basically fallen down as far as it would to get to the center of mass. So in the time it took to fall to here, it drifted this far sideways. And notice it's no closer to the Earth than it was when it was in its initial position. The only difference is it's now traveling in this direction here at a tangent to this circular path it's taking, and it's being pulled inwards this way. So in the amount of time it would now take to fall from here to here, it's going to drift this way all the way to here. So it ends up taking this path, and it falls all the way around this way, and it's in orbit. So the big takeaway is that things in orbit are basically falling. And Isaac Newton figured this out in the 1600s and drew this lovely depiction here. We call it Newton's mountain. It shows a cannon on top of a mountain, and the first shot doesn't have much perpendicular velocity, but each subsequent shot has more and more of this horizontal velocity perpendicular to the force vector. And you see shot G makes it to the south pole from the north pole, and then he shows this next one, which he labels, I guess, is it A or B? I'm not sure, but it goes all the way around. Essentially, Newton fires a cannon here. It falls all the way around the planet and then hits him in the back of the head. And then he just said, well, look, that's basically what the moon and other things are doing. So he realized that orbit is just a special case of falling. Let's see, what's next here? Okay, and now keep in mind, if I was to go back here, if I tried to actually do Newton's mountain experiment on Earth, it wouldn't work. And the reason is, as soon as I fired, it's going so fast, it's going to encounter all this air friction, and friction is a force that does work, so it converts the kinetic energy to thermal energy, and my cannonball would just turn into a meteor, heat up, burn up, and disappear, and it would also slow down and would fall to the ground. You can't actually do Newton's mountain experiment on Earth, not because of gravity, but because of air. If we were to go to the moon, it'd be totally possible. On the moon, there's no air, so I could fire a cannon. It would literally go all the way around the moon at that altitude. If I moved the cannon out of the way, it would just keep going forever in a circular orbital path. Now, the reason that we send astronauts into outer space is not because we're trying to get to a place where gravity is weaker. We're trying to get to a place where there's no friction. The truth is, most of our spacecraft orbit at an altitude of about 300 miles, and at that level, you really have only decreased the gravitational force on you by maybe 5% of what it is at the surface of the Earth. So gravity's plenty strong up here, but there's no friction. So once we give things that perpendicular velocity, they just fall forever. Now, let's think about this though. So the force of gravity is equal to the gravitational constant times the mass of a large object, the planet, the mass of the small object that's being attracted to the planet, divided by the square of the radius, or the distance between the centers of mass of the two objects. But it's also true that if we think about this, this is essentially, well, this is a better picture to look at. If I look at this one here, you notice that the object is traveling this way, its velocity is this way, and the gravitational force is this way. That seems really familiar. That's basically a centripetal force. The force is always acting towards the center of a circle perpendicular to the velocity of the object that's going around in a circle. So in this sense, the gravitational force that's pulling these two objects together is a centripetal force. So therefore, centripetal force, if you recall, is equal to the mass of the object that's going in the circular path times the square of its velocity divided by the radius of its path. So if we combine these two, if we say, look, the force of gravity is the centripetal force, so I'm just going to take this value here and put it over here. That gives me what I have right here. So now I have the centripetal force equals the gravitational force, and I can start canceling some stuff out here, guys. I can cancel out this m and this m for sure. Let's see, and then what I can cancel out is if I multiply this side by r, I'll get rid of that. When I multiply this side by r, the square goes away, and it leaves me with this once I've canceled everything out. And now if I want to solve for v, I just take the square root and I get this lovely equation here. This is the equation for circular orbit. So the orbital velocity of an object in circular orbit is equal to the square root of the gravitational constant times the mass of the planet that's being orbited times the distance of the object above the center of the planet that it's orbiting. And notice that the mass of the object in question is irrelevant in this case. It canceled right out. So let's just try using one of these. The orbit equation is here. This is one you'll definitely have on your assessment next week. So let's get comfortable using it. Let's try our next thing here. So let's try this. The moon has a mass of 7.3 times 10 to the 22nd kilograms. Here's its radius in kilometers. Now the problem is I can't use kilometers here. I have to use meters here. So I wonder how fast the spacecraft had to be going in order to enter circular orbit around the moon at an altitude of 10 kilometers above its surface. So unfortunately, I've got to convert the kilometers to meters before this is going to work. So what I have here then is G is 6.67 times 10 to the negative 11. That's the gravitational constant, times the mass of the moon. Here I've converted the radius of the moon and the altitude of the spacecraft. I've added them together and converted them to meters and got this. Notice I'm not squaring in this case. Remember that one of those r's got canceled out. There's no square here, unlike the gravitational force equation. And then I just solve for this and I get 1,692 meters per second. An object at this altitude traveling this fast perpendicular to the surface of the moon is going to orbit the moon in a circular path. So now I'm going to ask you to try doing this. I'll just skip over that for right now and go on to the next thing here. Okay, so when you have an object that has exactly this velocity, that is the velocity of this object is equal to the square root of the gravitational force constant times the mass of this times this radius, then the object is going to orbit in a perfectly circular path. However, what if I took this object and I gave it velocity, but instead of giving this velocity, I gave it a little bit less? Well, if I gave it a little bit less, what happens is it doesn't make a circular path. It falls a little bit close to the object and it comes back to where it started. So in this case, I just said, well, I'm just going to make this equal to 1/2 of gm over r squared. And by doing that, so I basically pushed it a little bit slower, and it didn't make it all the way around. Now notice it comes back to where it started, but the thing about this is if it has less than enough velocity to make a circular orbit, it makes an elliptical orbit, and in this case the initial position of the orbiting object is at the high point in the trajectory. Now if, on the other hand, I push it faster than this, now what happens is it overshoots the mark. Instead of going in a circular path, it goes too far and gravity gets weaker and it goes out far and it goes really slow and then picks up speed and comes back to its starting position. So in this case, I just chose to say instead of 1/2, I decided to go with 3/2. At this point here, it looks very similar. I have, again, an elliptical orbit now with the larger object at one of the foci. But in this case, instead of this being at the high point, it's at the low point. Now, is a magical breaking point. Now, one magical breaking point is this. Let's just go back to here. What if I didn't give it any horizontal velocity? What if I said this times 0? So instead of making this times 1/2 or 3/2, I made it 0. This all goes to 0. The velocity is 0, and all that's going to happen is it's going to fall straight to the ground. But if it turns out if I multiply by 2 or more, something weird happens. Once I get this value of 2, I've reached what's called escape velocity. And what happens there is it's going so fast that the gravitational attraction between these two objects is not sufficient to cause this to curve and come back around. So it just drifts away forever, and it never comes back to its starting position. It just drifts off, and we call that escape velocity. And we say it's escaped the gravity of the planet, but really, remember, the gravitational force between these two objects is never going to go away. It's going to exist all the way across the universe. It's just that it will never slow down and come back. So, for instance, the escape velocity of Earth's surface is 11.2 kilometers per second, or 11,200 meters per second. So what that means is any object leaving the Earth's surface, regardless if it's in a perpendicular path or straight up, if you leave Earth's surface at this speed, you're eventually, or less, if anything less than this, you're going to fall back to Earth. So if I throw something up in the air, and we're ignoring friction in this case, if I throw this up in the air at 11,000 meters per second, that's not quite escape velocity. It's going to go up, slow down eventually, and come back to Earth. However, if I throw it at this speed or faster, what happens is gravity never has a chance to quite slow it down. It slows down, but it gets farther away, and gravity gets weaker. It slows down a little bit more, but gravity gets weaker, but it never quite slows it all the way down to 0, and therefore that object has essentially escaped from Earth, and it's never going to fall back. So, for instance, the moon has this mass, it has this radius, and I want to know how fast the Apollo astronauts have to leave the surface in order to escape its gravitational pull. So all I have to do is remember that it's basically, I put a 2 inside here. Take the orbit equation, just put a 2 inside the radical, and you just solve it for r, and you'll find that you end up with this. You just substitute in 2 times g times the mass of the moon. I have to remember that this has to be in meters, and I get the escape velocity of the moon. Now, if I did it with the sun, so what if I tried doing a proportionality problem? What if I said the escape velocity from the surface of the sun is this, which is quite fast, okay? It's basically, I don't know, almost 600 times what it is on Earth. Now, what if the sun shrank to 1/4 of its current size? What would its escape velocity be then? So anytime I'm using a proportional change, I'm going to solve it using proportionality. I mean, I could look up the radius of the sun and divide, but I don't have that here. So instead what I'm going to do is this. Remember, I say, what am I looking for? I'm looking for the escape velocity. So I'm going to leave this as a v. Now I'm going to change to 1/4 the radius. So I'm going to take the radius and change it to 1/4 because it's 1/4 of what it was. Now this is 1 times what it was, g is 1 times what it was, and m is 1 times what it was. The only thing that really changed from being 1 times what it was is the radius of the sun is 1/4 of what it was. So I changed it to 1/4. Notice there's no squaring of it here, which gives me 1/1/4. And I take the square root of that, so that's basically the square root of 4, which is 2, which means the escape velocity of the sun, if it's 1/4 of its current size, is double what it is currently. Now, here's where it gets kind of interesting. The speed of light is 300 million meters per second, or 3 times 10 to the 8th meters per second. And nothing can travel faster than the speed of light. Light can travel that fast. Other things can travel that fast. You know, like the gravitational force can travel that fast. But that's the fastest anything can go. Well, it turns out as stars shrink and get smaller and smaller and smaller, they retain their mass, but they become denser, and the surface gravity gets stronger because the radius is getting smaller. And eventually you get to a point where the escape velocity exceeds this value. And at that point, that star turns dark. It becomes black, and we call it a black hole. Black holes are real. They're abundant in the universe, and they're a simple consequence of Newton's gravitational equation and combined with escape velocity. Now, so let's try this. So if the sun has this mass, 1.98 times 10 to the 30th kilograms, how small would it have to be in order to form a black hole? Keep in mind that the speed of light is 300 million meters per second. So in this case, I'm not doing proportionalities. I'm actually looking for an actual value. So what I'm going to do is I'm going to substitute in. I'm going to put for the velocity of escape velocity, I'm going to put in the speed of light. So when the escape velocity equals the speed of light, well, here, let's just go to here. I'm going to take this equation. For v, I'm going to put in the speed of light. That's the velocity that I'll have when it becomes a black hole. 2 is going to be a 2. G is 6.67 10 to the negative 11. Here's the mass of the moon, and I want to solve for the radius of the moon. So I just put things in, I rearrange them a little bit, and I come up with this. If the sun was to shrink to basically 293 kilometers in radius, it would be a black hole. Now, it turns out it doesn't have enough gravitational material to cause itself to shrink that small, but plenty stars do. So most stars, not most stars, but many stars when they die do become black holes. So that's really all I need to present to you today. I think you can do your homework if you have this. Sorry if this was a little bit rough, but hopefully this will get you going.